So this is chapter 2, part 4. And this part of the chapter, this is section 2.4 in the book, starts out with the basic NMR experiment. And this experiment is just a 1D acquisition where you have a delay, we call D1, a pulse, which I'm going to call PW, and then we say that we acquire data, so we'll call this AT. And these are all times. D1 is the time in seconds, PW is in microseconds, oops, I should say microseconds, and acquisition is a time again in seconds. And the D1 time, this is for to allow the spins to come to equilibrium. When you place the sample in a magnet. Or after a pulse. Basically at the end. Because what you're going to do is you're going to repeat this pulse sequence, because the NMR signal that you get is weak. And so what you're going to do is you're going to repeat this sequence n times. Repeat n times. Basically what you're going to do is you're going to do signal averaging. And the goal here is that your signal is proportional to your number of scans, and we'll call n the number of scans, and your noise is proportional to the square root of the number of scans. So basically your signal grows as the number of scans, but your noise only grows as the square root. So your signal to noise grows as n over the square root of n, which is equal to the square root of n. So you could think of it like this. Let's say you took 4 scans and you have some baseline signal to noise, and we're just going to call that 1. Okay? You can call it 100 or whatever, it doesn't make any difference. And let's say you wanted to double your signal to noise. The question is, how many scans do you need to do to double your signal to noise? We just say, well, I have a signal to noise baseline of 1, and we want to double it, but we know that we did 4 the first time, and we don't know what the number of scans is. And so if we solve for n, from that, you're going to say n equals 16. So we need 4 times the original number of scans to double the signal to noise. So it's not, you don't do twice the number of scans to get twice the signal to noise. You have to do 4 times the number of scans to get twice the signal to noise. And that applies to anything. If you had if you originally took in 16 scans and you call that your baseline of 1 signal to noise unit or whatever, and you solve for n, you're going to get 64 scans, which again is 4 times the original number of scans that you did. So always with NMR, if you want to double your signal to noise, you have to take 4 times as many scans. So that gets, and all this was back to this basic NMR experiment where we have a delay and then we have a pulse which excites the nuclei and puts them in their XY plane, and then we collect the data and then we repeat it over and over again, and the D1 is just to allow everything to come back to equilibrium after this pulse and acquire. But the reason why we had to do mini scans is because the NMR signal is weak and we got to do signal averaging. So the next part is just some nomenclature. We call anything that has to do with proton or hydrogen nuclei, we call that a homonuclei. And everything else is a heteronuclei. Heteronuclei. Stuff like carbon 13, nitrogen 15, phosphorus 31. Those are the typical ones that other people run. That's all heteronuclei. Some other things that nomenclature that you may run into, as you hear, like you have in an NMR experiment, you have an NMR instrument, you have many different channels, and each channel produces a frequency. So it's very typical to have 2 channels, channel 1 and channel 2, and channel 1 is dedicated to the high frequency nuclei, proton, and fluorine. And channel 2 is basically everything else. But typically it is C13. Because for an organic chemist, that's all you care about is protons and carbons generally. The next thing, oops, got my pen upside down, is coupling. So you can have homonuclear coupling, and so this is coupling between the same type of nucleus, and typically that is between a proton and a proton. And you can have heteronuclear coupling. And so that's going to be between 2 dissimilar things. And typically for organic chemists, it's between proton and carbon. So a homonuclear case would be like a 3-bond coupling constant between proton and proton. Something like this. So that's a 3 bonds, 1, 2, 3. Coupling constant between proton and carbon. Then heteronuclear would be a 1 bond, so a 1 bond CH coupling. And you would measure these with something like a HSQC experiment, which we'll talk about later, or if it's like a longer, say something like this, where it's 3 bonds CH, then you would use something like I'm thinking of the other thing I wanted, HMQC. It's another. These all give you the same information, basically. They're different, but they give you roughly the same information. And for a 3 bond, you'd use something like an HMBC. So heteronuclear multiple bond correlation. And so there's just some nomenclature to be aware of between homonuclear couplings and heteronuclear couplings. And generally, for proton spectrum, we like homonuclear couplings because it helps you solve the structure of the molecule. But for carbon spectrum, we don't like the heteronuclear stuff. Or I shouldn't say don't like, but we don't want heteronuclear. And we will tailor the experiment to get rid of those heteronuclear couplings. Because what you'll see is it doesn't really give you much structural information, maybe a little bit, but more of it's a nuisance. So if you had, say, a carbon with 3 protons on it, and you run the C13 NMR, you're going to have your carbon intensity spread over 4 peaks now because of this heteronuclear coupling. And so that's going to decrease your intensity, and it's also going to make the spectrum more complicated to interpret. And so generally we like to do it, and we'll do some decoupling sequence like Waltz 16 to get rid of the J coupling. Effectively, this pulse sequence sets J1CH equal to 0. That's the goal of the pulse, this Waltz 16. So you'll run a carbon spectrum, and then your net result will be, instead of a multiplet, you'll see a single peak, where this is, again, C13 on this spectrum, but we've collapsed the multiplet into one peak. And so we can count all the carbons and in our spectrum and get rid of a lot of the overlap that happens between multiplets.